No.
Okay.
It's toxic. That's great. But why you microwaving orange? It's really weird.
Okay. So what about this now? If we want to analyze this function, let's go through a couple of all the way through the whole thing. We want to fill the table out completely, and then sketch it based on the table. So you'll be amazed how much information you can fit on that table. It's the whole darn function is well described by the information you put on the table. So we got to have a couple layers here, right? We got to be able to analyze the function, its derivative, and the second derivative. Maybe. Second derivative is always optional, unless we're trying to find inflection points. If we have to find inflection points, and let's say we do. If we have to find inflection points also, then we do need the second derivative. If we're not looking for inflection points, it's optional as a way of testing first derivative critical numbers using the second derivative test, right? If we have a horizontal tangent line of the function, first derivative equal to 0, concave up, what does that have to be?
True.
So if I've got, let me say that again. So if I've got a function, if I've got a horizontal tangent line, point of tangency, and at that point, at that critical number, it's got to be a minimum, doesn't it? If it's concave up, it's got to be a minimum.
I didn't know if you wanted to.
If it's concave down, well, we don't know what we don't know what kind of function, but we know that that's going to be a relative minimum. If we have a first derivative 0 and a negative second derivative, that would be concave down, so that would be, right?
Maximum.
Maximum. Okay. So that's what the second derivative test would be good for in terms of analyzing relative extrema. But if we need inflection points, we've got to have the second derivative. So let's say we're going to do the whole shebang here. So we want second derivative, yeah. Okay, so now, last, right. Now, what about the original function? Let's look at the original function. Are there places where it is not defined? Where are those?
At 2.
And?
Negative 2.
Okay. And we get those where? Okay, good.
Random guess.
Right, we got a red flag here, don't we? We've got on the bottom of the function, we've got something that can't equal 0, right? Okay, so when we're finding the domain of this thing, we have to exclude those values of x. So we've got x squared minus 4 can't equal 0, so x squared can't equal 4, so x can't equal plus or minus 2, right? Okay, so we'll be able to add that. Those are the restrictions on our domain. What do we get there, by the way? What's going on at those places?
You get shenanigans.
Vertical asymptotes. Good, because at those values, the top is defined, but the bottom is not. A number over 0 means vertical asymptote. Okay, so we get vertical asymptotes at x equals plus or minus 2. Okay, that's useful. That's going to help. That vertical asymptotes are very helpful to us. They help us define how the function is going to look. Okay, what else about the original function? What else could we do? What about horizontal asymptotes?
Why don't we take the numbers like that in the top?
Okay, because now if I set the top equal to 0, all we're doing is finding the zeros of the function, which might be okay to do. I mean, that might be useful. If I knew where the zeros were, that would help me anchor a couple points on the function. So we could do that, but maybe that's not as big a deal. Asymptotes are really big. Asymptotes are going to infinitely big, in fact. They're going to really guide how the function looks. If we wanted to do this, we could.
Plus or minus 3.
So we don't have to, or?
I mean, it's probably not a bad idea if it's easy to do. It's really hard to find the zeros. I don't know if we really need them. Yeah, we'll get them, but we may not need them. X squared minus 9 equals 0 when x equals plus or minus 3. Okay, so there are my zeros.
The zeros?
That was that kind of, I don't know, it's kind of bungled up there. Okay, so now how about horizontal asymptotes? Okay, if we want to find horizontal asymptotes, how do we do that with our function? How do we find horizontal asymptotes with our function?
Okay, remember.
Clear out there. That's 3, 5, right?
Yeah.
Those are the limits at infinity.
Right.
Right? So we're just going to use that rule we just talked about. So the limit of f of x as x approaches plus or minus infinity would be the limit of... Now, what am I going to get here if I were to distribute the 2?
What the limit is?
What am I going to get on top?
2x
squared plus, we don't care. On the bottom, we're going to get x squared minus, we don't care, because that's what I'm looking at, isn't it? Right. So the leading terms. And what are they telling me about?
Does that mean there's a horizontal asymptote?
Yeah.
It goes to
Right, because I've got the same, look what I've got here. I've got the same.
But then we'll find out what those numbers mean over that.
Right. So those are the same values. So we know that this limit is equal to 2 over 1 equals 2. So our horizontal, say it again.
Now, how would we find out what numbers mean?
Well, now that's where we have to end up doing the calculus. Okay, so this, we haven't done any calculus.
Now we do calculus.
None of this is calculus right here. All we've done here is we've just looked at pre-calculus stuff. We've just analyzed. What's that?
What's finding the limit considered? Just algebra?
I mean, yeah, pre-calculus. Like, analysis is what it really is.
So we just analyzed it. Or we
So horizontal asymptote is y equals 2. Okay, that's pretty good. We got a lot of stuff there. Okay, but now we can start doing the calculus. We got to find relative extrema, points of inflection. So we're going to take our original function, rewrite it here.
I don't remember what it is.
X squared minus 9 over x squared minus.
Okay, we got to differentiate.
Now we do. Goes into motion rule? Nope.
Yes.
Yep.
So let's differentiate that. What do I do?
Okay.
Yep.
We found the
Found vertical asymptotes and horizontal asymptotes. And we found zeros too. Yeah.
And so
Say it again. Because all that's going to tell us, well, let's see what that does tell us. If we wanted to take this information, you guys remember what these are, please. Plus or minus 2. 2 is the, and then, okay. So if we want to graph this, let's do that. I need to... Just click that.
You can, but did you do that? Okay. So I didn't.
Vertical asymptote, they got 2 and
I knew he was going to do that.
vertical is plus or minus 2.
Okay, good. So we had...
Red. Can we do red? Red?
Yeah. I'm going to go by 2s.
When you told us that we didn't have to do it all again. Yeah. That's what we
You have to change it to
You're on vertical. Yeah, you're not making a big vertical difference there.
Okay, so what do we get then? We got,
Tic-tac-toe on X's.
so we got, there's...
the horizontal was that 2.
Yeah, what are you doing?
Yeah, I'm going by 2s.
I said 4.
No, there's 1, 2, 3.
Oh, okay.
1.
Okay, now I get it.
Just so I can spread it out a little bit.
Oh.
So there are the asymptotes, right? So now, what do we know about that? Well, we know basically what this thing has to do in these areas, but we don't know anything about extrema or points of inflection or things like that, right? Lots of things could be happening for example, in here and in here. We just know what happens way out there and way up or down there, right? Yeah.
Well, if it has to touch the x-axis, -3 would be.
Oh, true. Okay, and we know those two don't. We know that we had zeros there and there. So probably it's doing that.
Yeah.
Probably, but it might do this. What if it goes? It's probably not, but it might go. It might go something like that.
It's not.
Right.
Not doing that.
It doesn't seem quite complicated enough for that.
You led to the fact
But
that
it
it's
can
not
crouch
going to,
horizontal.
so it's not going to.
Yes, right. So it could go like this, right?
Not doing that.
Okay, but we'll see. We'll see. We'll see what it does. So now if we go down and do the derivative, what do we get from our derivative? What's the rule that we have to follow here to differentiate this big piece?
Derivative of the bottom times derivative.
BU prime.
No,
Bottom,
Yeah,
derivative of the
both
top,
times UB prime.
okay,
not times.
times.
Should be prime times.
Derivative of the
Prime.
top is,
Okay.
I could pull a 2 out in front of the whole thing also if I
Yeah,
wanted.
you could, but.
Or I could just leave it in, either way. So if I differentiate the top, what am I going to get? 4x, okay,
You good.
minus the top
Good.
times the derivative of the bottom, which is
Oh, okay.
divided by the bottom squared, which we'll just write like that.
Okay.
Because, I mean, the reason we're doing that is, maybe, why expand that when we really want to have it factored anyway? We're eventually going to want to, say that again.
Haven't we always done that though? Rather than expanding it?
Yeah, we don't want to expand it.
Okay.
Right,
Yeah.
right. Okay, so then if we simplify this, I can, distribute the 4 and I get 4x. 4x cubed minus 16x squared. You know what I should do though first? Let's not do that. That was kind of dumb. What can I do that'd be better than that?
I wrote in pen, thanks.
It's all good. What did you do before?
Well, I started to distribute, but yeah, good. You ever hear that? That was a good idea. The idea was, why not take out a 4x? I want to factor the top anyway. So let's pull a 4x out of each term,
Oh, just X.
leaving me with x squared minus 4. Now, minus, right? I took out a 4x. That leaves me with minus that quantity.
Yes.
Okay, I'm going to pause there. Does everybody see that?
I don't understand.
I'm gonna wait till you finish though because I am writing pen.
Okay, somebody. Okay, Anna's going to explain. Why did we do that? That was your idea. It was a good idea. Yeah, because ultimately, what are we going to do with the derivative? Ultimately, with the derivative, we're going to want to be able to set the top equal to 0 and find the zeros. So it needs to be factored to do that, right? And set the bottom equal to 0 to find where it's undefined. Okay? So why, looking ahead here,
How do you get plus that?
because if I take away, if I divide out a 4x, that's leaving me with a minus 1 to get distributed, right? Does that make sense?
Yes, sir.
I'm dividing away from each of the two terms a 4x. Well, if I divide out a positive 4x, I'm left with a minus 1 times that quantity. So I'm just going to distribute the negative 1, which changes those signs.
All right.
Right? Okay?
Yes.
Ethan, does that make sense? Okay, well, for example, watch this. What if we did this
I don't want
instead?
to take up all your time.
No, that's good. Well, what if we did this? What if we had,
I don't want to be a
I'm not
jerk.
seeing this.
I don't want to learn.
3x squared minus 6x minus
4,
3, 2,
9.
6x times the quantity a plus b.
Ooh.
The a plus b is going to be now,
Can we just make your soup for this?
if I want to factor out a 3x, what am I left with? Well, this is going to give me x minus 2 times a plus b, right? Because from this term, if I divide this term by 3x, I'm going to cancel the x in part of the 6, right? Right?
Oh,
So that's the same thing.
one time. Oh, gotcha.
Gotcha, okay.
Figured it out.
Okay.
Gotcha.
Bingo.
Light was like, yep, got it.
Did it. Didn't know that.
Okay, so then so that's the top. Bottom's already taken care of. So we could combine like terms in the top. I'm going to get x squared minus x squared. That cancels. Negative 4 minus 9 is negative 13.
Yep.
Right? So then my final answer for the first derivative is just 4x times, 4x times negative 13, which is what? Negative 52x?
Sure. Although I don't know.
Definitely negative 52x.
That would really.
Divided by x squared minus 4 squared. Okay?
Yeah.
Good. Now, if we didn't need the inflection points, is that something we would want to differentiate again to get?
Nope.
No, absolutely not. If all we needed to know was what's going on at where the relative extreme are, then we would find the critical numbers from this and use the first derivative test, because that's a hard derivative to take. If I have to take this again, that's a lot of work to do a second derivative.
Yeah.
Only when it's really easy to do would we go ahead and take the second derivative so we could use the second derivative test, right? But here, unfortunately, we need it because we need the inflection points. Okay, so let's grab this and go to another page.
What's your theory?
What?
Okay, well, while we're at it, let's find the first derivative critical numbers. Now, where do we look for critical numbers? This is real important. Everybody watch this very closely. We look where the first derivative is 0, and where else? Where it's undefined. Okay, now where is the first derivative undefined?
When the bottom is plus or minus 2.
When the bottom is plus or minus 2. But recall from our earlier work that we already know we have vertical asymptotes there. Okay, because the function is undefined at plus and minus 2, there can't be critical numbers there, right? Those are just artifacts. The fact that our derivative is undefined there is a meaningless artifact of our function's non-existence there, right? So we don't have to. I mean, those are not critical numbers. They're vertical asymptotes. Vertical asymptotes trump everything, right? So there is no place on our derivative where we're going to have to look for those. There's no. Let me say this again very clearly. There's no place in our first derivative where we'll get critical numbers where the derivative is undefined, because those numbers are already off limits. Does that make sense? Because that's really important.
So you can go back and read that last
So let me say that again. If I'm finding the critical numbers plus and minus 2 don't apply because the function already doesn't exist there.
Oh yeah. Because
Okay.
they were.
Critical numbers can only have to be values where the function's defined for them to really be critical numbers, right? Okay, so that's kind of nice. We don't have to worry about those. Instead, we can focus just on the places where the function's undefined, the derivative function. So this equals 0 at where? Where the numerator is 0, which is when? When x is 0, sure. Right, because that's where 52x would, or negative 52x would equal 0, when x is 0. So we get one critical number right there. Okay. Okay, so if we go back to our table, let's go ahead and add that information. So let's put in we got our x, y prime. And we got a couple things here. We knew, for example, that at x equals 3, whoops, I got that backwards. At x equals 3, y was 0, and at x equals negative 3, y was 0. So there's an ordered pair, and there's an ordered pair, right? We also found that at 0, at x equals 0, we had a 0 first derivative. So that's a horizontal tangent line, right? Okay. Now we got to go find out where the inflection points are. Okay. By the way, do we know, by looking at this function here, see if anybody can tell me using non-calculus stuff, if you can tell me what that critical number at 0 has to be.
Say that again?
I want to know what's going on our table here. We'll find this other ways too. We can always use the first derivative test, for example. But is there a way that I could know what's going on here?
Test points.
I want to know, yeah, but even without, is there a way, just by analyzing the function itself, is there a way that we could know what's going on there? Or what's, well, what it is? Is it a maximum, minimum inflection point?
Isn't it 0? 2.
Look at the function. Right here. It's kind of messy, but look at
You
that.
plug in 0?
What do you notice about all the powers of x?
They're straight.
They're all even, aren't they? There are no odd powers of x. So what does that tell us about the symmetry of this thing? If I plug in a negative value of x,
Even rid of a negative number.
yeah, it's not going to change it, is it? If I plug in 3, I'm going to get the same answers I'd get if I plugged in negative 3.
Right.
Because the only place the x's show up is where they're squared, and so plugging in a negative value, you can get positive anyway. 3 squared and negative 3 squared are the same thing, aren't they? Right? So that's our test for even symmetry that we talked about a little bit this year, but more last year maybe. Remember, our test for even symmetry we defined like this. I'm just going to throw this in here now because it fits. So even symmetry is when f of negative x equals f of x. Remember that stuff? If I plug in a negative value for x, I get the very same thing back that I started with. Okay? And even symmetry means symmetry about the y-axis. So folding symmetry about the y-axis, right? Okay. So then one more time, if this thing has folding symmetry about the y-axis, what's going to happen in here? Could it be an inflection point? Could it do this?
No.
No, because it's got to be able to fold on itself,
Can
right?
you make sure, can you just let inflection point is when it
Changes concavity from concave up to concave down. So an inflection point would look maybe like this, right? Where over here it's concave up, over here it's concave down.
So
concave
inside,
up you can't see, but concave down.
Right, concave up means it's catching water, means that a tangent line sits below the curve. Concave down means a tangent line sits on top of the curve.
Concave
Yep,
up.
got it.
Yeah, concave up means it's bowl shaped up. Okay? Yeah.
does that mean in the middle between the two vertical asymptotes, does it mean that there's a function also touching 0, but it's concave down?
No, this horizontal asymptote doesn't apply in here.
Okay.
No, asymptote means way out there. In the
Way-
middle, that doesn't matter.
way
It's
out.
only way out there.
Haven't we decided that those are the only 2 points where it crosses x?
Yeah,
So it has to go up and not touch 0 and then go back
right.
down?
Okay, it has to. Wouldn't you agree here? And this is, I mean, this is. I know this is kind of scattered here, but I want to try to bring in all these disparate elements so we can see how this thing builds up in different ways. You know that because it's got this folding symmetry about the y-axis, it has to be a minimum or a maximum, doesn't it? It has to be, right? Because it has to fold on itself. So one or the other. Now, what's the value of the function always going to be? Look at the value of the function here. We could just look at the function and say, okay, as x approaches, when is it going to get really, well, is it going to be positive or negative always?
Negative.
Look at this thing. Oh, or at least for big values of x, what are we going to get?
Positive.
It's going to be positive, isn't it? Right? Does that make sense? If I put in a value, if I put in a value of,
10.
I can't have big values of x. Bad choice. If I put in a value like 0, okay, if I put in a value like 0, what's the sign going to be? I'm going to get negative 9 over negative 4, so that is positive.
Negative or
Okay,
negative is negative.
okay. So it's this thing is going to be concave up, isn't it?
Yeah.
If I get really close to
Oh, yeah, that's.
2,
Wait, okay, what?
So the country above it's going to be.
Oh, okay, okay.
Side
Okay,
is
negative.
like on symmetry.
right? Because if I go, well, maybe I said that wrong. Hang on. If I choose a value close to 2, the bottom is getting what? Close to 0, but negative, right?
Right.
The top is going to be negative, so it is positive, yeah. Right? So we could reason our way through this. That's my point. Just by looking at the behavior of the function. Now, we don't have to do that, though, right? We've got better tools for that.
So
Yeah, calculators.
Critical point, it starts there and then goes up and then it's reflected and then it goes the other way.
Right.
My calculator.
Right.
can do all of
Exactly.
this.
Okay, so now let's use calculus. We have to do the calculus anyway. It's a lot easier. Remember what I said, it's the further you go down in the table, the easier it is to analyze what's going on, right? So let's get our second derivative.
But wouldn't there be nothing in between the two lines on the bottom and just have a...
Just be only on the top,
Yeah.
yeah.
So can you draw that?
Well, we will. When we're done, we'll sketch it, yeah.
What are we trying to find?
We want to find what this thing looks like. We're analyzing this. We want to know what's going on with this thing. Where does it have extrema? Where does it have inflection points? Stuff like that, okay?
Yeah.
So second derivative time, all right.
We're pretty much being the calculator right
I thought you said we're not going to do the second derivative.
No, we need inflection points, so this time we're going to, yeah. So unfortunately, we got to do the second derivative. All right, let's go ahead and pull the negative 52 out front this time. Okay. And what do we get? How do we approach this one? We're going to have to, well, we could. We could put the whole thing on top and use a product rule. Why not?
Or
Let's
you
do
could use
that.
the quotient rule, like we just did earlier.
Could do that.
Well, it would be easier.
Here's a suggestion. I like it. Minus 52x times the quantity x squared minus 4 to the negative 2. So now we can use a product rule. We can just go ahead and let's leave the negative 52 out front, okay, and differentiate. We could have used quotient rule also, but we'll do this.
Just for sake of difference.
So we're going to do the 1 times the derivative of the other. Let's go ahead and do the second one first this time, so we can have a positive term first. X squared minus 4 to the negative 2. What's the derivative of x?
0,
No.
1.
1. Okay, times 1 plus the first times the derivative of the second. Now that's a chain rule issue, isn't it? Because I got a power,
idea,
right?
Shut up, Matt.
Whoa. Man, I'm just getting violence.
Okay, so I bring this out in front, right? Okay, so negative 2 times what? If I'm taking the derivative of something to the minus 2.
X, 2, 1.
Negative 2 something, right? To the what power?
Three.
Negative 3. Okay, negative 2 something to the negative 3. The something is an x squared minus 4. Okay, now what's the derivative of the next layer? 2x. Okay. Okay.
So we should have done the quotient rule, right?
No, this is probably better.
Why?
Because, well, look, you don't have to, I mean, it's about the same in this case, but this is just as good, if not better. Because you only have 2 terms, and you don't have to remember that you subtract between the 2. You can't screw the product rule up.
Unless you're in.
Okay, so then we get minus 52. Now, can we factor anything else out here?
No. X.
That didn't make any sense.
Okay, I could pull out an x squared minus 4. Now, you gotta be careful with this, remember?
Right.
When I'm factoring like bases out, I have to factor out the smaller power, the least power.
Yeah.
So what's smaller, negative 3 or negative 2? Ah, okay. So I'm going to factor out an x squared minus 4 to the negative 3, leaving me with, what?
Hey, what's your YouTube channel?
What are we going to get here? If I divide away an x squared minus 4 to the negative 3, how many are left?
1.
1. Good. X squared minus 4 to the negative 2
Factored that out.
minus negative 3. Yeah, we factor that out.
So negative 2x. Or negative.
Being serious.
Okay. Plus, now what's left over here? This is completely gone.
That cancels out.
So I'm going to get a minus 4 x squared. Right? Yeah.
No.
Yeah, that's good.
Well,
Okay, and then if we write that, let's write this as a quotient, right? So that's going to give us, let's see, that's going to give us, let's go ahead and simplify, well, on the bottom, what do we get? This stuff goes to the bottom, right? On the top, if I distribute my negative 52, I'm going to get a minus 52 times negative 3x squared minus 4, right?
right.
Plus.
Right? Good?
Yeah, getting all this?
So, okay, is this an actual question? Is this the right question?
Yeah. Yeah, they're long questions. Okay? And so while we're at it here, why not also, why have a negative times a negative? Why not distribute the negative and make those positives? A little better.
Okay.
Okay?
So
there's the second derivative. Okay, now we got to find the second derivative critical numbers. Where is the second derivative undefined?
bottom is 0.
When the bottom is 0, right? But where's the bottom 0? 2 minus 2, off
We
limits.
can't do that.
Off
So
limits.
let's find the top.
Right. So we just want to find where the top is 0. Now, where is the top 0?
X is 0.
We have to think about this for a second.
The square root of 4/3.
Square root of negative 4/3.
Ooh.
Right?
Right.
Now look at this. We know that the top, this equals 0
algebra. Come on.
when
Plus or
3x
minus the square root of
squared
negative 4/3.
plus 4 equals 0. So that's when x squared equals
Plus or minus.
negative 4/3.
So.
So nowhere for no real values. Right?
Yeah, those
you
are
can't
not
do square
real.
root of a negative number.
Right.
What does that?
Even root of negative.
Okay, so we get no critical numbers of the second derivative.
So
Right.
why do we?
Okay, you with me?
So it doesn't have no inflection points, right?
So it has no inflection points. Right. Okay. Inflection points
You
can
can
change
straight
concavity,
lines.
where the second derivative changes sign.
Concavity, that's what I have. Just a refresher.
Literally 3 times.
So what about, now we got the second derivative, so let's use the second derivative test. If we want to know what's going on with the first derivative, we want to find the sign of the second derivative there, right? If this is the second derivative, our only critical number from the first derivative was at x equals 0. So we just want to know then, we want to know this. We want to know what's the sign of f double prime of 0.
The sign?
Yeah, the sign.
Okay,
So let's play our little sign game. Now,
Come on, guys.
There's no humor in it, though.
okay, so what's that give us then? 52 is positive.
Right.
This factor is always positive.
Yeah, you're right.
It's always positive value. What about down here? If I take x equals 0,
It's always going to be negative.
okay, if I take, it's always going to be negative, isn't it? Right?
If I take the sign.
You would do. Right. So we get 0 minus 4 is negative, a negative number to an odd power.
Positive or negative.
Right. Right. So the second derivative,
Oh my God.
is negative.
I had the wrong sign.
Close lips.
You get my humor.
I got you.
Yeah. Aside clown. Indifferent.
So then, maybe we did this wrong the first time.
Oh, God.
I don't know. But anyway, that's negative, isn't
Yeah,
it?
disregard the first name.
So if it's negative, our non-calculus approach might have backfired on us. What is
Boy,
this?
this is out of the book. How are we getting this wrong?
Well, oh no, something went wrong. Something did go wrong.
Oh, gosh.
Hang on. Something went wrong here. Up.
This is good. We can find what we want. Yeah.
Yes.
I want to play a game.
Yeah. Yeah. Okay, what happened here with... Welcome to the real world of math.
Mr. Oya, in the real world of math, there are no errors.
No, in the real world of math, it's all about making tons of errors and figuring out where
If
you're
you have an error, just do the cosecant of it. Right?
Just say what Yan Yan
So
said
if I
on
take
Saturday.
4x out, minus x squared. Yeah, that's right. Isn't it?
Maybe the book is like Yan Yan.
There are no errors in math.
Yeah.
There you go.
Eva makes a valid point.
That's what I said.
There are no errors in math because math isn't real.
Okay. Hang on, do you guys...
Where do you keep getting?
Where did I mess up? Where did we mess up?
Wait, were we supposed to get positive?
Sure. Yeah.
Okay, go to the bottom. What number were you supposed to plug in for x?
0. Wasn't 0 our critical number?
Yeah.
Yeah. So... something's
You
messed
can use
up.
your critical number for the first derivative.
Right. The second derivative test looks at the concavity of the function at the first derivative critical number.
Why is that positive?
Okay, maybe that's where the mistake is. What I meant to do here, maybe I messed up. Oh, hang on. No, it is negative. I got the negative.
No, but you need positive.
Yeah, why'd you make all that
Right,
positive?
because what I did, these were all negatives.
Yeah, why? Why?
Distributed.
So I distributed, I multiplied,
Yeah, negative 1.
Don't you have to do
Yeah.
the top and bottom
So
side
where's
of
the
it?
error then?
no, I just distributed this negative 1.
Across to those.
Oh.
See?
So where's the error?
I'm not seeing it.
We did it right.
Oh my god.
Well, you find it. Get back to us and let us know.
Well, that's the one I just did. So it should be,
Maybe
no, it's got to be positive. Well, maybe I just look at their work and see if we did something wrong.
This is negative.
Oh, we got different first derivative than they did.
How?
Did I write down the
Yeah,
wrong
'cause we did the quotient or the times rule. Not,
No, it shouldn't matter.
That was the second.
Shouldn't
That's the
matter.
second derivative. The first derivative we did the.
Okay, that's wrong. Something's, let's find our mistake. What did we do?
Easy.
so we started with the wrong equation and did everything wrong.
Oh, you know what? No, we didn't. Okay, so if we differentiate this, now let's find this. Let's find this.
Confusing me.
Okay, so we use quotient rule. So we got the bottom
Just run the debug.
times the derivative of the top, which is 4x. Okay, minus top times derivative of the bottom. Good. Okay. We
Distributed one.
factored out a 4x, leaving us with x squared minus 4, minus the quantity x squared minus 9. Minus x squared plus 9. Good. Over the bottom squared. Okay. So,
Wait. Back down 4x. That x doesn't go with it.
so why do they get 20x? And we don't.
So maybe the book's wrong.
No, we're wrong.
How can you get this?
What's going on?
Isn't the x supposed to go with it, right?
That's what I was thinking.
Yeah.
Oh. No.
Why not?
Minus x squared.
Hey,
See, that should be a plus 9.
that's what I was thinking.
What did I? Oh my
From
god.
the very beginning, I was
Look what I
thinking
did.
that.
Whoops, this is a little embarrassing.
Wait, what?
Negative 4 plus 9 is what?
Positive.
Definitely positive
You
5.
said 13.
There we go.
Dang it, Oya!
You did basic math wrong.
Yes.
At least we found the error.
And Oya fails at arithmetic. Class over.
Okay, so
So amidst 45 minutes, 45 minutes of calculus, we managed to do 9.
No. We actually.
we haven't even done one problem, but that's the way it goes sometimes.
We just did like a tenth of one problem.
So you see that's gonna change that sign, right?
Okay. How?
Yeah,
It
we got
now hold up, shh, quiet please. If that would have honestly changed the specifics, but the behavior wouldn't have changed because all we did was we just changed the constant on top, right?
Exactly the same.
Yeah.
Everybody agree?
Yeah.
Okay. So I'm not going to redo the whole thing. We know.
No, I'm not going to be here if you do.
So we get plus. So if we go over here to our table, if that's a plus sign, It's a happy face, right?
Yep.
Okay, so then
We knew that from the very beginning. Why would we do all that work?
to do it the calculus way. So if x is 0, what's y? Negative 9 over negative 4, so it's what, 2 2 1/4. Okay, we got that, right?
Yep.
Okay,
That's
well,
what I said it was.
I'm going to leave you hanging then until
Ooh,
next
cliffhanger.
time. We'll get the rest.
Wait, so that goes down to 3 or 2? 2. That makes more sense.